Welcome to today's class, and today we'll be dealing with the RLC circuits, particularly under alternating current part 2. And I'll share my screen now, and we'll begin the class as soon as possible. I implore you to pay rapt attention. So I'll be discussing some very basic concepts that are very important for your exam. Yeah. So once again, alternating current part 2. I'll start with explaining what it means to have a resistor circuit. Let me start with the resistor circuit. What I mean by that is when you draw the diagram of that circuit, you have a resistor. That's the sign of a resistor. Then you have, on this side, you have your switch, or sometimes they call it the key. Then you have your AC. This is your AC, your alternating current source. Then it's connected to your resistor. So the only resistance in this circuit is the resistor. So this is a resistor. We'll call this a resistor circuit. Now there's another kind of circuit we call the capacitor circuit. The capacitor circuit. And in this particular circuit, you have your diagram. You have your capacitor somewhere here. Then you have your switch. You have your AC. And then it's connected right to the capacitor. In that scenario, what you just have is this your alternating current, it gives you an RMS voltage. So your alternating current attached to it is an RMS voltage. So keep that in mind. This is the capacitor right here. So there's also another one called the inductor circuit. So let me first of all title the entire section we're talking about RLC circuit. But they exist in their own individual they can exist individually and together. So if they are existing individually, this is the resistor circuit, this is the capacitor circuit, and this is the inductor circuit. So in the inductor circuit, you have this kind of setup. Most of the time, they put something like this for the inductor circuit. That's like the sign. Its own is like a more coily, instead of the zigzag pattern. The one for resistor is kind of zigzag. The one for inductor is kind of coily. So just take note of that. So that's how it is. Then we have a normal switch or key, and then we have our AC, and it's connected to this is the alternating current, which has a RMS voltage. So this is what each of them look like individually. But when I want to draw them together now, or let's start pairing them 2 by 2. Let's have a RC. Let's start from RC. RC circuit will look like this. RC circuit will look like this. It means a combination of resistor and capacitor. So if I combine resistor and capacitor, I have the zigzag pattern, then I have capacitor, then I have my switch, and then I have my AC connection where my VRMS exists. So this is my AC. So this is what a RC looks like, because this is a resistor and this is a capacitor. So that's the idea. Let's just go step by step. There is another one you can have that is called the RL circuit. RL circuit. And in that particular concept, you have the resistor itself, you have the inductor, okay, which is more coily. Then you see your switch, you have your AC, and then when I say AC, it's alternating current. We started from this in the first part of alternating current. This is the second part. So I'm introducing you to the concept of RLC, but we have to go from R individually, L individually, C individually to them 2 by 2. We have done RC, we've done RL, and I think we're left with LC. So there is another one we compare. Let's see. Hold on for now. Okay, we have RL and RC. Yeah. So let's not do LC. Let's go straight. Once you have RL, RC, we have to do RLC. Let's do RLC. So leaving out the fact that you can have LC. So we only have RC, RL. So something must be combining with R, then RLC. So RLC circuit, this time you have all three of them together. So and this is what it looks like. You know that this is R, then L is coily. And when we say L, that's inductor now. You know, this is R, this is L. Should have written the symbol there. L is for inductor. So you see it, RL, then C, R, L, C. Then connected to our switch and also connected to our AC. So this particular guy, we know that it is key or switch. So this is how the RLC circuit looks like. Please pay attention to that. Now we can go into talking about some other important formulas. At any instant, when you have just the resistor, for just a resistor circuit, we follow Ohm's law. Which is V equal to IR, right? And so the I in that circuit will be V over R. And the meaning of that is that since we have V to be equal to V naught sine WT, it means we can write I now as V naught sine WT over R. That's a very good, formula when you just have your resistor alone. And then recall also that we know that our I is equal to I naught sine WT. So at the end of the day, we'll discover that we can also write, we've known this one from the last class, this particular formula, we know this one from last class, we know this one from last class. So we only used V inside here, then we obtain this guy. So now we can also say, for IRMS, it will be equal to V RMS over R. How did I come about that? I know V equal to IR based on Ohm's law, and I know I will be what? V over R. So even the RMS values too, they will still follow the same principle. IRMS root mean squared will equal to the voltage root mean squared divided by R. So it is important to note that for a case where you just have resistor, let me underline that in red. For just a resistor circuit, you must note that the current and voltage, are in phase. So when you just have only a resistor in the circuit, the current and voltage are in phase. So take note of that. They are in phase. And the meaning of that, what does that mean? It means that the maximum and minimum values are obtained at the same time. So let's just keep it as simple as that. Now, what have we just done? We've just discussed a case where you just have for just a resistor circuit. Now we can go to a case where we just have for capacitor, for a capacitor circuit. And in that case, you can also call that capacitance in an AC circuit. So that's the idea. Now, once you have it that way, this time around, let me just start from the discussion of the fact that voltage and current will not be in phase. Current will lead voltage. So you will see a phase diagram like this. And when we say something is leading, it will always be on the x-axis. So we have current, the capacitance current will lead the capacitance voltage by 90 degrees. So the guy here is always leading. And we say the one here lags. So we can write it that when you are in a capacitor circuit, or when you have capacitance in AC circuit, the current leads voltage by 90 degrees. So keep that one in mind. So when I'm writing the formula, that particular statement I just made will show its influence. That is, you would have something like, normally we know that voltage is V naught sine omega t. But we can now write, because current leads, we write current as I equal to I naught sine omega t plus 90, which is pi over 2. So in this case, you just have, in voltage, you just have omega t. But in this case now, you have omega t plus 90. So that's what we mean by current leads. So please take note of that. The capacitor is another opposition to the flow of current. Now, I could have mentioned that quite at the beginning, that when we say RSC circuit, we're talking about all these three things. They are all oppositions to flow of current, oppositions to current flow. Yeah, so that's how it works. They are all oppositions to current flow. The common one you normally hear of is resistor, resistor, resistor. But this particular alternating current part 2 is meant to introduce you to the fact that we have other oppositions like inductor and capacitor. So we've described a case where we have just the resistor. If you have the resistor, we just follow Ohm's law. And Ohm's law, you follow this pattern. And then we follow, we introduce the AC voltage. We write it. We write this. Then the relationship between the AC voltage and the AC current is that the current is equal to this divided by resistance. So, and then we also know that the RMS is described by this. So, but in the case of capacitor, this is first the establishment. We have to establish this first of all, that the current leads by 90. And once we have established that now, we can now establish something called, we can define capacitance. Yeah. Now, in this particular scenario where you have just a resistor, you see that we went with Ohm's law, and resistor has a value of R called resistance. But in this case, what are we going to call it? We are going to call that value for that the opposition. Let me write it. The opposition offered by a capacitor to the flow of alternating current is called capacitance. So that's like the opposition offered to the flow of alternating current by a capacitor. It's called capacitance. And the formula for capacitance is like, we use an X. Xc is equal to 1 over 2 pi. This is it. Fc. So that is the, oh, let me do it like this, sorry. This C here, let me adjust something in this definition. The opposition offered by the capacitor to the flow of alternating current is called capacitance, capacitive reactance. Let me put the capacitive. So just make the adjustment. Capacitive reactance. Yeah. One of the reasons why, and that capacitive, so let me write a bit. This is the capacitive reactance. Capacitive reactance. Take note of that. F is frequency, and that one is in hertz. While C is capacitance. That is the value of the capacitor. So capacitance, the value of the capacitor. So the opposition offered is called capacitive reactance. Please take note of that. So that being said, we have we can quickly now establish, like I said, this capacitive reactance is like, in the case of resistor, it's like that your R. Now we normally know that V equal to IR. So but now what is replacing R in the case of a capacitor is XC. So for a capacitor, I'm just used, by the way, I just explained using this. So for a capacitor, when a capacitor is in the circuit, the V will now be equal to IXC. Do you see what I just said? In a resistor circuit, what you have is R. But in a capacitor circuit, what you have is capacitive reactance. So that capacitive reactance will replace R and will now have V equal to IXC. So you see that? So what you now have now is that you can plug in this value of XC that you have here into this place for V. So you now have V equal to I into 1 over 2 pi FC. So we can now write it as, can write it as V equal to I over 2 pi FC. So either ways, once you know all these little formulas like this guy, and then this guy, once you just know even this one, that you can easily just plug in XC value into it. So those are the important things. Let's quickly do an example to make sure that we're following. Example. The question says a 2 microfarad capacitor is connected directly across a 150 VRMS 60 Hz AC source. Next, to find A, the RMS value of the current. B, the peak value of the current. So take note of that. Now let's analyze what was given to us first. We are given 2 microfarad capacitor, that is C is equal to 2 microfarad. And the meaning of that is 2 times 10 raised per minus 6 farad. Because micro is like, that's it. So taking note of that, then we'll now go on to say, okay, it's connected directly across a 150 VRMS. So that means the VRMS here is 150, right? 150 volts. You have your F given to be 60 Hertz. Now, what do you have to do? We know that we want to find, first, they ask us to find IRMS. That's the RMS value of current. We know that IRMS that's what they ask us to find. We know that V equal to IR. But we know that in this case, we don't have R. It is a capacitor. So it is V equal to IXC. So let's find XC first of all. XC is 1 over 2 pi FC. We know from above, right here. So we can plug in all that we have. We now have 1 over 2 pi times 60 times 2 times 10 is per minus 6, based on what we are given. The whole thing there will give us 1324.4 ohms. So that's another thing to note, that XC is measured in ohms. XC is measured in ohms. So because it's resistance offered by a capacitor. So take note of that. Having established that, we can now plug XC back into this place. We have V equal to IXC. But what are we looking for actually? We can now even write this as VRMS equal to IRMS XC. Are you following me? So we can now write IRMS will now be VRMS over XC. So we already have VRMS from the question, which is 150. 150 over XC 1324.4. That gives us IRMS as what? 0.113 ampere. That settles the first part. The second part now says we should find the peak current. If you go back, say find the peak value of the current. Peak value is more like I naught. And we know that I naught is equal to, we know that from the formula that we established in the first class, alternating current part 1, we say I RMS is equal to I naught over root 2. So that means I naught will now be what? Root 2 times I RMS. So what happens is that root 2 times what we just got right here, 0.113. So once you multiply those two together, you have 0.160 ampere. So please keep that in mind. I want you to try this classwork right now. I'll continue the class, but this is a very important one for you to do. Determine the RMS value of the current in an AC circuit with a 5.5 microfarad capacitor across a 220 VRMS 50 Hertz. So keep that in mind. That helps us to conclude our discussion on capacitor. We have talked about just for capacitor alone, for resistor alone and capacitor. Let's now go to the discussion on for inductor. For an inductor circuit alone, or wherever it appears, wherever it shows up, this is it. So for an inductor circuit, we can quickly also define, or let's establish just the way we started in capacitor. We said in capacitor circuit that current leads, so it's the one on the x-axis, the voltage lags. So I will now create the formula. So, but it's opposite now in inductor circuit. In inductor circuit, it is voltage that leads. So inductor will represent by L. So voltage leads is on the x-axis, and current lags. So voltage leads, current lags behind. So the meaning is that when you write V RMS now, and is by 90. So when you write V equal to V naught sine WT, when you are writing for current, you write it as I naught sine WT minus pi over 2. So, and there are two ways to write it. You can either write it as V naught sine WT plus pi over 2. Yeah, that is because this one leads by 90. And then if you write it like this, that means current will just stay as I naught sine WT. But if you write current like this, you have to subtract that 90 from, if you write voltage like this, rather, you have to subtract that 90 from current. If you write voltage like this, by adding the 90 to it, you leave current the same way. In either case, the explanation is that current leads by 90. So you are either adding 90 to it, or leaving it like that. When you leave it like that, you must subtract 90 from current. You see what's happening here? So let me write this better. Let me just rub off what is here right now. I've explained it, but let me write it better so that you can get the idea. So you can either write it like this. So current voltage leads. That's what we know. So you can write it as V equal to V naught sine WT, and then the corresponding current is I naught sine WT minus pi over 2. So that's when you have the voltage like this. Or V equal to V naught sine WT plus pi over 2. And that the corresponding current for that will be sine WT. So these are the two ways to write it. In both, you will discover that voltage leads by 90. That is, when you write the voltage normally, you subtract 90 from the current. Or when you add 90 to this, you leave the current as it is. So either ways, voltage is the one leading. So take note of that. So let me remove these arrows from here. So having said that, let's now go straight to talking about the opposition offered. The opposition offered by the opposition offered by an inductor to the flow of alternating current AC is called inductive. Just the way we had capacitive reactance. This one is called inductive reactance. So, and is represented by this time around XL. And this time around, the formula is 2 pi FL. You know, in the case of capacitor, it was 1 over 2 pi FC. So here it is 2 pi FL. So take note of that. Please, these are important formulas. So that now leads us to talk about how will I write the voltage. Voltage is normally IR. But here now, since it's inductor, R will be replaced by XL. R will be what? Replaced by XL. And so if R is replaced by XL, we have V equal to what? IXL. And I can write that as I times 2 pi FL. So V will now be 2 pi FLI. So that's how it works. Just take note of all of that and keep things going. Let's also note that the unit for inductor, that is for L. The unit for XL is ohms. The unit for L itself is Henry. That's inductor. For an inductor, the unit is Henry. And yeah, we already know that the unit for frequency is hertz. And yeah, so just keep all of that in mind. Let's quickly do something like this. Let's find, and most of the time when they're asking you to find resistance offered by either a capacitor or an inductor can be regarded as impedance. So keep that in mind. Can be regarded as impedance. Let me take one example of a question like that so that you get used to it. So a question says, let's say this is another example. The question says, find the impedance across an inductor of 0.2 Henry inductance. Put it like that. The question put it like that. Just question is to enlighten you on how the question set normally appears. So find the impedance across an inductor of 0.2 Henry inductance when an AC voltage of 60 hertz is applied across it. If the voltage is given by V equal to, this is a very interesting question, V equal to sine 120 pi t. Calculate the RMS and peak values of the current. So let's analyze what we have in this question, and step by step we dissect the solution. Find the impedance across an inductor of 0.2 Henry. That is, they giving us L to be 0.2 Henry. They said when AC voltage of 60 Hertz, 60 Hertz is the frequency. So we write it down, F is 60. Applied across it. If the voltage is, they now give us a formula for the voltage. V is 150 sine 120 pi t. That's what is there, 120 pi t. Now, they're now asking us to calculate the RMS and peak values of the current. They're asking us to find RMS and I naught. Now, just note that this particular V they gave us is VRMS. It's the root mean square one. So, or let's do it like this. Basically, okay. Let's try to find W. Yeah. Okay. Okay, let's go step by step first. This particular voltage you are given, I can compare it to my AC voltage formula, V naught sine omega t. Yeah. And from there, I will say V is V. I will say V naught is 150. I will say my omega is 120 pi. So let's establish those things first. V naught is 150 volt. Yeah. So particularly, this is just a structured formula of the voltage. I won't call it VRMS per se, because we can find VRMS on our own. So just keep that in mind. Yeah. Then omega, that is W. If we do comparison here, we discover that it is equal to 120 pi. And that's very accurate. Yeah, because based on our normal formula, we know that omega is 2 pi F, and F is 60. So it is correct to say 2 pi times 60, and that's very accurate to have 120 pi. So that corresponds, that's okay. So what we particularly need here is we've gotten V naught. We can use the formula that says V RMS equal to V naught over root 2. All right. So V naught over root 2, we can easily say, okay, 150 over root 2, and that should give us some kind of approximate value of 105. So once we know VRMS, it's very easy to get IRMS by doing this. And what do we have to do? V equal to IR. But you will notice that in this particular circuit, what we have is not R. What we have is an inductor. So what we have is inductance, and we can use inductive reactance. So we can write our V as IXL. So instead, you see that R has been replaced by XL here. So let's find XL. We know that XL by formula above that we have expressed is 2 pi FL. So we can find out 2 pi times 60 times L has already been given to us as 0.2. 0.2. Then when we do all of these multiplication together, we should arrive at 75.4 ohms, something of that nature. Ohms. So, and that's the symbol for ohms. So now we have all the tools we need to find I, because we already know, like I said before, V equal to IXL. We know V, or let me put it like this: we can write it as VRMS equal to IRMS XL. So that will leave us with IRMS that we're looking for will now be VRMS over XL. And in that case, we can easily have can easily have VRMS is 105. I've already found it, VRMS to be 105 right here. So 105 divided by XL 75.4. So IRMS is going to be some kind of 1.99 ampere. Now, having found IRMS, it's so easy to find the peak value because we can say IRMS, we recall that it's always equal to the peak value divided by root 2. So we can easily say, okay, go ahead and say, right, that can allow us to write it this way. Oh, this division right here, 105 divided by 75.4, I made a mistake. That should be 1.39 ampere. Yeah. So then the RMS value will now be, so the RMS value is 1.39. We're looking for the peak value. Yeah, let me write this first. I naught will now be IRMS times root 2. So that will now be 1.39 times root 2. This will give us 1.99 ampere. Or, another way to find the I naught value is to say, okay, I know that V equal to IXL. So V naught will be equal to I naught XL. So I naught will be V naught over XL. So we already know V naught to be 150. 150 over XL is 75.4. So 75.4. And then that should give us just around the same thing. So the idea is that you could use, either this or this to find the I naught. But you saw the way we got the IRMS. But in order to get it, we had to find XL first of all by doing this. So just break down the examples like that. That's your duty, to go home and analyze how the examples were done. And from there, master the most important formulas. I'm moving straight ahead into the next thing. And that is, well, before I go on, I will give you a classwork, just like I gave you after the first example. And that classwork is to determine, your duty is to determine now the RMS value of the current, in an AC circuit, with, I gave you the inductor here, with a 5 Henry inductor across 220 volts, RMS, 50 hertz. So please take note of that. Now, I will now consider, you see, basically we have considered, what happens in an inductor, for an inductor circuit, as was right here. Consider that. We considered what happens in a capacitor circuit, as right here. We considered the simplicity of the resistor circuit. Yeah, that was right there. And now, let's consider what happens when 3 of them combine together. What kind of resistance will we have? You know that when it is just a resistor, we have resistance. That's basically it. When it is just capacitor, we have capacitive reactance. When it is just inductor, we have inductive reactance. Now, when you have the 3, it's impedance. Yeah, we also said that in some questions, they will call, those ones alone, they will call them impedance. You understand? So they will call them impedance. And what they mean by impedance is just that particular resistance if they are alone. For instance, in this place, the impedance was, in this particular example now, the impedance was this guy, because the only thing in this circuit was just the inductor. So in this case, the impedance was the same thing as, because we only have an inductor, the impedance was the same thing as the inductive reactance. But we are now going to a case where we have the three of them together. So that's more like an RLC circuit offering impedance. That's the combined resistance. And let me quickly just go into that by saying what we have as the impedance. When it was for, let me just revise alone. For resistor alone, R is R. We have R. For inductor, we had something like XL. For capacitor, we had XC. When you combine them, we get something called impedance, and it's written as the square root of R square plus XL minus XC square. So the idea is we have a diagram like this, XL here, XC here, and we have R. So the impedance is more like the resultant of this. So this is like the vector diagram from which we get this formula for where Z is called the impedance. So this is the vector diagram, and this is the important formula here. This Z is the impedance. That's how you find the impedance. Now, what if we now want to start talking about voltage and the other things? We know that normally we say voltage equal to IR, right? But when you have a combination of these things now, R is replaced by Z. So you have voltage equal to IZ, and so voltage equal to I into bracket, what was Z? Square root of R square plus XL minus XC square, and then all of that. So that's the idea. So you see that, right? So now our I, so this is the formula when you have everything combined for voltage. And then you can easily write that our I will now be voltage over Z, which is R square plus XL minus XC. I believe you don't need to cram all this. You just need to know this one, then know the formula for Z. Then you'll be able to produce any one. So let's quickly also write formulas like that. That means that we now have I. So once we have established this now, we can easily write I RMS will be V RMS over Z. I naught will be V naught over Z. That's when in a RLC, when you have everything combined for RLC circuit. So keep that in mind. We can now define impedance because we need to define it in words. Impedance Z is the overall opposition of a mixed circuit containing a resistor, an inductor, and or a capacitor. What we mean by that is that you will still see, probably in the next class, you will consider a case where we have them being considered pair by pair. We might do it in this class if we still have time. We do it pair by pair. Or we do it, So he said overall is offered by mixed circuits containing resistor and inductor. Let me just put and a capacitor, okay? Just take note of that. It is also measured in ohms. It is also measured in ohms as well. So take note of that. Yeah. Let's have a question to typify what we've discussed so far. Yeah. Let's have an example. We'll take like 3 examples. Yeah. Then we'll call it call it a wrap for today. Let's take this set of examples. So your notes are very important here. Have any confusion, you revise, go back to your notes, you see the formulas that apply. Number one, find the RMS value of an alternating current whose peak value is 5 ampere. Now that's a very straightforward question. I'm going to give the solution as we know what they mean by RMS and what they mean by peak value. By now, you know the formula that applies here is that they're talking about current, right? So I'm saying I RMS be equal to I naught over, and we know that I naught is the peak value. So we're saying they gave us the peak value as 5 amperes. So we're saying 5 over 2, and definitely that gives us 3.53 ampere. Yeah, 5 over 3. Yeah. That is, if you press your calculator right, you should have that. Yeah, 3.53. So let's go to the next one. In an AC circuit, the peak value of the potential difference is 180 volts. We're now being asked, what is the instantaneous potential difference when it has reached 1/8 of a cycle? So this is a very, very important question. The best thing, like I used to say, the best thing before you attack a question is to analyze the parameters that are available, the parameters that are actually exposed. Now, in an AC circuit, the peak value of potential difference, that is V naught. Solution. V naught is given as 180 volts. We're asked what is the instantaneous PD. They are asking us actually for V equal to V naught sine omega t. They're asking us for this guy. This V is instantaneous PD when it has reached 1/8 of a cycle. And what do they mean by 1/8 of a cycle? They are trying to tell us that, oh, the angle here, WT, which is like sine something, sine something, this angle, they're telling us that WT is equal to 360 over 8. One cycle is 360. But they're telling us that this particular circuit has reached 1/8 of a cycle. So they're telling us that that angle is 360 over 8, which is 45 degrees. And so we can now say V will be what? V naught is 180 sine 45. That will give us V as 180 divided by root 2. So that is going to give us, if you remember what we do with SOD, whenever you have SOD here, you rationalize. Do this. So that can be written as over 2. So that's 90 root 2 volts. And we can call that question a wrap. For question number 3, another example, a circuit consists of a resistor, 500 ohms. And a capacitor, 5 microfarad, connected in series. If an alternating voltage of 10 volt and the frequency of 50 hertz is applied across the series circuit. Calculate the reactance of the capacitor. Then calculate the current flowing in the circuit. Then calculate the voltage. The voltage across the capacitor. And then there's another part to that question that says, the B part, the B part says, if the capacitor is replaced with an inductor of 150 millihenry. Millihenry is like 10 raised by minus 3. Millihenry, calculate the impedance and voltage across inductor. Okay, that's okay. We'll break this question down and we'll finish it up. Use that to wrap up today. Solution. A circuit consists of a resistor of 500 ohms. Let's know that first. R in that circuit is 500 ohms. Then a capacitor 5 micro, this is something like a U, microfarad, 5 microfarad. So the capacitor there, C, is 5 microfarad. And the meaning of that is 5 times 10 raised by minus 6 farad. So we have R and C in this circuit. When I say if an alternating voltage of 10 volts, what do they mean by alternating voltage of 10 volts? You can write that down immediately as V. Let's write it as V, 10 volts, and frequency F, 50 hertz, is applied across the series circuit. Calculate the reactance of the capacitor. Now, they also calculate reactance of capacitor. We know that is XC, and that is 1 over 2 pi FC. So we go 1 over 2 pi. F is what? Times 50. Then C is 5 times 10 raised by minus 6. By the time we do that calculation, we have 636.62 ohms. So that is what they asked us to find first. The second part of the question says we should calculate the current flowing in the circuit. Now we know that V equal to IR. So we can easily say I equal to V over R. This question already gave us V as 10. But we cannot categorically just say R is 500 now, because in this particular circuit, there are two oppositions, R and C. You get what I'm saying? R and C are the two oppositions. So we need to find something now called, let me write it as impedance. So whenever you have two, whenever things are not alone, whenever you have combination like R and C now in this particular circuit, it's not going to be R again. We need to replace, let me write this for you. We need to replace this by V equal to IZ. So Z becomes the combination. So I will now be V over Z. So let's find Z first. Z in this case now is normally supposed to be square root of R squared plus XL minus XC square. But in this circuit, we only have C and R. So there is no L. So XL will be 0. So if XL is 0, we say Z can be written as R square plus minus XC square, because that's 0 minus this. So we know that when you square a negative number, it is still positive. So we can write this now as Z equal to square root of R square plus XC square. So we can easily find Z by doing, we know our R to be 500, R square. We have already found XC, 636.62. 636.62 square. When we do all of that math and find the square root, we get Z to be about 809.5 ohms. So that's the combined resistance in that circuit offered by the resistor and the capacitor. And now we are good to go with finding I, because I equal to V over Z. V in this case, we have already said V is 10 on the question, but we just found Z to be 809.5. Very interesting stuff. That leads us to an answer of 12, or let me write like this, 0.001235, which we can write as oh no, this is, sorry, excuse me. Yeah, this is it. It's 0.001235. And this we can write it as if we want to convert it to milliampere. This is the answer. This is just the answer. This is the answer itself. But if you want to write it in milliampere, you can multiply that by, if you multiply that by 10 to 3. So if you want to write it in milliampere, just in your jotter, multiply it by 10 raised by 3 and write it like this. That's in your jotter, or don't write it somewhere in the book. So whatever you get, you now write, we'll get 12.35, you now write it as milliampere. So you heard what I said. So that's how to operate. So then the next part of the question says we should find the voltage across the capacitor, which makes things easier. V equal to what? IZ. You know that in this case it's not R, because we have a combination of what? Resistor and capacitor. So we now have I is already found to be 12.35 milliampere. That's times 10 raised by minus 3. Then we are multiplying that by the value of Z. That Z is 809.5. You know that this 12 times 10 raised by minus 3 is the same thing as this guy right here. So we just wrote it in terms of milliampere here. So I can write this as, it's still the same thing as saying 0.01235 times 809.5. That's IZ. So that will give you your voltage value as a, hold on for a bit. Oh, the question was specific. It said the voltage across the capacitor, please. So it cannot be Z. It was specific. So let's cancel that. That's a very important question. It said voltage across the capacitor. So if it's voltage across the capacitor, we have V equal to IXC. What this question was asking you specifically, across the capacitor. So we now have, so you use the current up there, that's 0.0123, which is the same thing, whether you write it in ampere or milliampere. So, but you must, if you are writing 12.35 milliampere, you have to multiply times 10 raised by minus 3. So I mean, that will still give you this. So what my point is that this is the current. So that this is it. We just express it in milliampere here, that's not a problem. That's just, and I told you that in order to express in milliampere, go to your corner of your note, multiply by 10 raised by 3. That's because at the end of the day, your 10 raised by minus 3 will cancel the 10 raised by 3. So that's just the idea. Just follow the rules. But in essence, I is this. Then we have XC. If we go up, we must have found XC somewhere. They must have given us, we found it here, 636.62. 636.62. That gives us a voltage across the capacitor to be 7.86 volt. So move to the B part of the question. And what did the B part of the question say? It said, if the capacitor is replaced with an inductor, and they gave us that inductor 150 millihenry, they say we should calculate the impedance and the voltage across the inductor. So they gave us an inductor of 150 millihenry, and the meaning of that is 150 times 10 raised to the power minus 3 Henry. They now say we should calculate calculate impedance and voltage across the inductor. Impedance and voltage. Impedance, they are asking us to calculate impedance and voltage across the, I would love to hear what they said, across the inductor. So now, the point is they ask us to calculate impedance first and then voltage across inductor. So now the point, what we'll do is, okay, let's find, and now they said L replaces, if L replaces the capacitor, so now that means we're having R and L. So because R is in the circuit before, you know, the circuit composed of R and C before. So if L replaced, if an inductor replaced the capacitor, we'll now have R and L, of which you know that R was already 500, you know, it's up here, ohms. Now we have L to be 150 times this, that's 150 times 10 raised to the power minus 3 Henry. We can quickly find, we know that impedance formula is square root of R squared plus XL minus XC squared. In this case, the capacitor is gone. They say it no longer exists. It has been replaced by an inductor. So here is 0. So we now have Z equal to R squared plus XL squared. So we now have 500 squared plus, let's find XL. XL is given by 2 pi FL. So 2 pi F in the question initially was already given as 50. And then L is 150 times 10 raised to the power minus 3. And that will give us about 47.12 ohms. If we put that here, 47.12 ohms squared. So that will give us, hold on. So once we do all of that math, should get something. I think I have to grab my calculator. Give me a minute. So let me plug that in. 500 square plus 47.12. So please, whatever I'm doing, confirm with your calculator. So I could make algebraic mistakes. That's fine. So this will give us 502.21 ohms. So take note of that. So now we found the impedance to be 502.21 ohms. Now we have to find the voltage across the inductor. Now that's like VL. VL equal to I, instead of IR now, is across the inductor, IXL. So I in this question, we already know that I is, we have found it to be, yeah, no. We have to find a new I. Yeah. So the new I will now be, hold on for a bit. Voltage across the inductor. Hold on for a bit. Let me see. We already have the main V. Okay, good. VL is this. No, we know that V is IXL. So let's find I. In this case, this is how you find I, V over XL. We've gotten XL to be this guy. So this V is the V in the AC circuit itself. That was the one given from the beginning. Yeah. V in the AC circuit, the alternating voltage. So that will now give us down here 10 over XL is 47.12. When you do that, you have your I value to be 0. Let me see. Oh, hold on. Sorry. Yeah, the V in this case, since we have a R and when we're finding V for this, yeah, I see. It's XC. Okay, good. So the voltage we're looking for is actually, yeah, the voltage across, let me write this first so that you don't get confused. The voltage across inductor that we're looking for is going to be V equal to IXL. But before we can find that, we must find I. And how do we find I? We must use I from the general circuit, V equal to IZ. And we just found Z, right? We found Z up above here, 502.21. So I will now be V over Z. That's 10 over 502.21. So that's 10 divided by 502.21. That gives us 0.0199 ampere. So having found that, now we can now do the voltage across inductor. Now we can now use that formula, V equal to, which I can call VL, equal to IXL. So now we now use that I, 0.0199 times XL is 47.12. So keep that in mind, 47.12. So that's how it works. So please, you have to go down, look at your notes, look at the procedure we're doing, and master it. This is your work to read now. You've been taught, you need to study. That will give us 0.9377. Yeah. Vote is voted now. Vote. So it's vote. So please take note of that. This is why we call it a wrap, and I will see you in the next class.